together. So we look at T cells and MHC. So, similar to the B cell, the T cell also has an antigen receptor. The T cell receptor for sure. So there's a T cell receptor called PCR. And as you might expect, there's a lot of similarities between the TCR and the PCR. And that's because these lymphocytes, these T and B cells, are derived from a common lymphoid precursor. So there's a lot of things about those T cells that have in common. And one thing, they have very similar structures. So you can see, here's the antibody up here. See this arm of the antibody here, which has the T. That's exactly the same size as T cells. Same size, and they go into a whole family of protein family members. The T cell and B cell receptor, they both have variable chemistry domains. They both have an antigen binding site, which is this, in the case of the T cell receptor, it's a membrane distal region protein. Much in the same way as the antibody binding site is sort of furthest away central area. And they both use the same recombinase activity to rearrange the gene. And there's those similarities, there are some differences. Vector doesn't do all this fun stuff with the antibody. There's no somatic fragmentation. Big differences with the T cell receptor cannot bind free antigen. It has to have the antigen printed to it on the surface of an antigen presenting the cell. So that's what it is. So the T cell receptor doesn't bind to the whole antigen. What it binds to is actually a peptide derived from the chains of the peptide. Then to do it in the context of a things we have to look at today. One is the T cell receptor, the other side of the equation is the MHC molecule. A little bit about surface markers. We use surface markers all the time, like cell phenotypes. We divide all the T cells, mature T cells, and the T tracks are either C or there are double positive ones, or anti, but they're immature T cells. We only see that they're developing thymus, thymocytes. And then double positive. CD3. That's associated with the T cell receptor complex. It's kind of analogous to the signaling protein associated with membrane bound with the globulin. The function is distinct. The T cell receptor itself doesn't direct signal into the cell itself. It does it through actually a complex electrical pulse. That's CD3. I wanted to show you this diagram here. CD3 is a bit of a peculiar one gamma chain is one delta chain, there's two epsilon chains, and this one. That whole complex is called CD3. So, like I said, those are responsible for the signaling into the cell, and they're held by these pluses and minuses for the static interaction. On the cytoplasmic side of the CD3 complex, there are all these antagonists. Except tyrosine kinase activation. So these get stable signaling. We're going to look at these CD4s and CD8s. Look at CD8s first, because there's only one CD8 cell. It's called a killer cell or a cytotoxic T cell. Very immune in a second. But the key features of these cells is that they have these granules inside them. Granules contain these components. So perforin is the next letter. Holes the membrane of tumor cells or viruses. Those holes allow granzyme to series proteins to enter into that target cell, and that triggers a cascade that culminates in the apoptosis of that target cell. So the cell is killed by this cellular, not like necrosis of cells for cell context. This is a very organized cell death where the cell is attacked or something that blends. And those are endocytosed by children. So in this movie, it's quite busy, but so what we need to look at is these little red spots that over the granules, and this target cell here is a tumor cell. And what you'll see is there's actually an interface there between the T cell and the target cell. It's like a synapse. What happens is those granules, you'll see that they'll relocate to the synapse, or deliver their cargo into the synapse space and make the whole granzyme go. See the tumor cells start to go apoptosis. So you see the granules are moving into the synapse there, and the target cell of characteristic. So these are very important cells. So CD8 cells are involved in killing tumor cells and virus infections. CD4 cells come in all sorts of flavors. We encountered some of these. These are all different types of subsets of CD4 cells. So we've got Th1 cells, Th2 cells, 17 T follicular alpha cells, and government centers. Plus, the end here called Tregs, regulatory T cells, suppress T cells by other T cells. Whereas all these other ones are active and they do different things. The Th1 cells are quite interesting. They produce a signature cytokine in interferon gamma. Interferon gamma is very important. Phagocytes, they internalize bacteria like mycobacteria. From Th1 cells to kill those like bacteria. Oftentimes, mycobacteria can like macrophages with impunity, unless they get help from the Th1 cell. And what you can see the MHC molecule on the surface of the macrophage, and it's presenting those bacterial Th1 cell. And in response, that Th1 cell is producing gamma interferon, and that helps the macrophage kill the cellular bacteria by a process that's called the respiratory. Respiratory burst is a way that the macrophage generates things like hydrogen peroxide, superoxide anion. So that's the function of Th1 cells. Follicular alpha cells, we heard about them on Tuesday. These are important for helping B cell make antibodies. So again, the B cell has got an MHC molecule on the surface, which presents the help in the form of co-stimulation and cytokines. Switching, so it goes from IgM to IgG or the other isotypes, and it's going to start secreting those. These are important in immunity to work. Receptors on the surface of mast cells that bind the Fc regions of IgE, and those are important for parasites. So Th2 is quite important. Burning immunity. Th17s, I don't really been around for a while. We've only particularly involved in immunity, probably play a role in experience. So they're all specialized for different things. T-regs obviously will turn off other T-cells. So it's actually an important part of down regular. Oh, I have to turn it off again, otherwise you'll get chronic inflammation and damage. So turning off is just important. Kind of analogous to what we saw on Tuesday. We're going to look at T-cell development. This is the same diagram. So all these cells that we find in the blood, right from bone marrow to cytokines, today we're going to look at this, T-cell cytokines. I just want to point out that there's what these cells down here, dendritic cells, and those are antigen-presenting cells. Back to the dendritic cells are super important. T-cell. They start as bone marrow cells, but then they migrate to the thymus. That's why they're called T cells. These cells are called B cells because actually they were first discovered in birds and they have a special organ that bursts in the bushes. Also developed in the bone marrow. So they're called B cells because they develop in the bone marrow. T cells develop in the thymus. So they're thymus dependent antigen cells. So they leave the thymus and then they undergo maturation in the thymus. And after that, they then leave a mature T cell and they circulate around the body for antigen, just in the same way as the B cell does. So they go through secondary lymphoid tissues. So we're going to look at both stages. We're going to look at this intrathymic development process first. So this is the thymus. Clinical diseases like the jaw syndrome, defects of the thymus, and they're using the T cell. That was it. Assuming you have a thymus, you can have the environment there to allow your T cells to develop. And there's no B cell area in the thymus, it's all T cells. But we have these regions that are divided into the cortex and the develop. So the cortex is actually the outer layer, if you like. And the thing is generated from epithelial cells. What kinds of epithelial cells inside the thymus? So we have cortical epithelial cells, we have medullary epithelial cells. Bone marrow derived cells, including dendritic cells, cells, and absolutely jam packed inside the lumbar there. Scanning the inside the thymus, you can see this the stroma. This is connective tissues that form cells. In between, we've got all these thymus cells that are going maturation. There's three important things that happen to the thymus cell inside the thymus. Those are very important things here. So the first thing is actually they don't follow the stages. They kind of overlap. So one of the important events obviously is this T cell receptor gene here. They call it alpha and beta. Because the majority of T cells are alpha T cells, so they have an alpha chain. There's T cell receptor gene rearrangement, and then there are two selection processes. One is positive selection, and then one is negative. To do that, I just wanted to compare the repertoire. Remember we talked about repertoires? So the repertoire, everything in blood Tuesday, this was actually a bit of a table, but it essentially says the same thing. You know, you have these multiple B gene segments, you have diversity segments in the case of heavy chain, you have all these other mechanisms. Version of extranucleotides in between the junctions. And then just by pure mathematics, you could work out the B gene junction of diversity. diversity segments of the extra nucleotides that stated. And you want to end up with a repertoire cells. It's a little different. There are a lot more joining segments for one. And so the repertoire is significantly greater. So there tend to be 18 possible each one having its own specificity. So remember, this is the way that the immune system has evolved to cope with the infinite variety of so it's kind of analogous to what we saw on Tuesday with the cells. So we have two loci. That was the chain. So there's a germline configuration. It's a non-functional gene. It's just collection of gene segments, just in the same way we have the arrangement to produce a functional B gene segment. So one B gene, one diversity, one joined together essentially at random to produce a unit of J. Diversity is only in the heavy chain. Describe translated protein expressed associated. So the sequence of events starts with the arrival of the binding site. So it arrives from the bone marrow as what's called a double nutritive, so having no sequence or a single. First thing that happens is the pizza chain undergoes rearrangement. Rearrangement is then assembled. That rearranged beta protein chain was assembled with a surrogate alpha chain. Remember the T cell is effectively has a rearranged chain with a surrogate alpha chain that allows the thing to be transported to the surface. Check. The receptor has the functionality that it's required. So what it has to do is it has to encounter the MHC molecule. These receptors are generated potentially randomly, and they're not all going to bind. A lot of these rearrangements are wasted. Don't get any signaling through CD3, then signaling through the T cell receptor. What that means is it recognizes either a class 1. So once it's past that stage of the process, it then becomes called a double positive. So that's successful, then you do alpha chain rearrangement. That's tested, of course, and that's functional. You then alpha chain. It's just a chaperone that allows it to turn the cell. It's transported with itself to it's not part of the functional receptor, it's just it's functional to allow that out. It's not part of the actual receptor. Then if that's successful, you have this double positive alpha beta thymus cell. Once you have that alpha beta receptor on the thymus cell, whether that thymus cell then goes to the next stage. And that's really determined by It's from the avidity of the receptor. So the avidity is a mixture of things, both affinity for the peptide MHC and the actual number of molecules, so the binding deep overall. Avidity of that rearranged alpha beta receptor for the MHC is what determines the fate of the plant cell. So if it's a good, healthy, moderate or strong either side receives survival signals. That's what's called positive selection. But if the binding is actually very weak, then this process produces a whole variety of different receptors. A lot of them are just non-functional. So CD4 and CD, we'll come to the difference between CD4 and CD8. That determines whether they were class 1 class 2. Not only dominant, a single positive has CD4, not CD8, or CD8 not CD8. So all mature. So in the fibers, the double positives are the ones that you only find double positives in the plant site, and then eventually they'll become single. So the ability of that T-cell receptor MHC strong interaction that T-cell the binding site will survive. But if it's a weak interaction, it doesn't survive. In fact, most of the T-cells often in thymus. But before they leave, the thymus sites have to become a single population. We said with the thymus sites are either CD4 or CD8, and both. So these double positives have then become single positive. And that's really determined by whether that T-cell receptor has an affinity for either MHC. So those receptors that recognize MHC class 2 molecules, here we have CD4 and CD8, and it's got a T-cell receptor that's reacting or binding to class 2 MHC molecule. That CD4 molecule is what's called a coenzyme. It binds to the outside of CD4. What's the interaction? So CD4 binds to class 2. Like I said, this is dogmatic. CD4 always binds to class 2. If that's the case, it retains CD4 and loses. It's called a class 2. The other side, we've got MHC1. With a T-cell receptor that has an affinity for class 1 MHC, CD8 molecule, co-receptor, that binds to the outside of the CD8. So it's co-receptor for MHC class 1, and that T-cell will then lose CD4 and express it. It either becomes CD4 or CD8, depending on whether that T-cell has an actual. That's one it becomes CD8. Now we have a T-cell that has undominant arrangement. It's become a CD positive. The next step the MHC molecules are presenting peptides that are derived from their own antigen. These aren't foreign virus-derived peptides. These are peptides that are derived from the cell. Last thing we want to do is let a T cell through that recognizes cell. So this negative selection step is the way the immune system is evolved to discriminate self from non-self. You remember the innate system uses a pattern recognition, like the polycycle. Next, all these billions of different receptors, and it weeds out the ones that are, let's say, reactive. Different receptors, and then it weeds out the autoreactive ones. And again, it's based on ability. So there's lots of cells that can do this and can find this. Before thymocytes sort of go to the cortical region and down through into the medulla. It has to run the gauntlet of so there are cortical epithelial cells, there are medullary epithelial cells, and worst of all, if the immunity is too strong, and this was all demonstrated 30 years ago in transgenic whole conditions where you can find peptides, they can know the affinity. If you have a very strong interaction, which was, in previous time, but over a certain ability, those cells are meant to kill off. Because those are the ones that are potentially going to kill them. We don't want to kill off. The ones that bind too weakly become paralyzed. They're kind of a sweet spot. I don't remember what we think to do, but there's just about right, and that allows that cell to go through and become a mature. If single positive thymocytes are tested for reaction to cell, placed again. There's probably also. There's an enzyme, the autoimmune regulator gene, encoded by this autoimmune regulator. I think different antigens that are expressed what's called in the periphery, that's outside the plant, expressed in plants. So those self antigens are expressed in plants. They're not just iron antigens, but that is expressed. Any autoreactive T cells that recognize antigens. Yeah, it sounds like a very clumsy system, right? If you make all the job, not 98% fail this process. Only 2% of thymocytes that they can through this process. And it's not a perfect system, but we still have all the do that. So it's not perfect, but for the most part, it's one message that I want you to get is here. After the T cell has gone through the spinal selection process, the positive selection by negative selection, with this kind of first infinite self-reactive cells, and that means that the rest is recognized. Very different strategy in primary system. Another thing to say is that those T cells will only really respond to antigen when it's presented to it in the context of the MHC molecule. Everybody's different. Their MHC molecule, unless you have an identical, your MHC molecules are different from the person's. So, your T cells will only really work with your antigen. Self-MHC is different. Sorry? What do I mean by what? Monergic? Oh, sorry. killed off, they're just paralyzed, so they're unable to. Under certain circumstances, they can be deactivated. So that's the maturation in the finals. So we're going to now look at what happens in the group. It's very similar to these cells. We've gone through this process shown on the left, and now going to traffic around the body in much the same way that we said. And they're going to go through. You need these processes, otherwise, if it was just random encounter between a T cell. That's done using these. They leave the thymus and they traffic through the secondary lymphoid tissues. And on the right here, you can see it's actually very similar to the way. So they enter in these lymph nodes, so the T cell entering the through the trach and the artery. How does it encounter antigen? Well, before we get to that, let's just mention that the T cells use the same homing receptor. Yeah, so it's the same homing receptor. The cells, in fact, they follow gradients to the same human. So, human tactic cytokines allows the pain itself to stick to the inside of the pain between those the itself and the antigen get there? Well, it really depends on the size of the antigen. It's very small, like a soluble protein, or it will just get carried away and just find it. So you have a lesion in the skin, the antigens can either just get into the fluid in the cell and drain into the immune system. Bigger than 200 to 500 nanometers, talking to bacteria cells. Those get picked up by special cells in the skin with layers. Actually, dendritic cells, they're like different names. So they're dendritic cells. These are bone marrow derived Langerhans cells, so dendritic cells, not to be confused with these molecules, and they have those long processing and they collect antigen. So those are follicular dendrites. What we're talking about, different dendrites. They're bone marrow derived, and they have a very special property which we'll see in a second. Either way, if it's either soluble or carried by the dendritic cell, it enters in through the lymphatics. You can see this sort of lymphoma. The dendritic cells carrying antigen will reside in this T cell area, and the T cells coming into the lymph node will be called naive. We call them naive, and they're attracted by the chemokine. So these green ones are called naive T cells. So they mature, but they just want to be exposed to antigen. And they will, hopefully, they will variants. They have a appropriate T cell receptor. And if they encounter that antigen on the surface of the dendritic cell, they become activated, those T cells proliferate and get swollen lymph nodes. That's relevant. T cells and B cells swell up. Once they become activated, they lose that homing receptor, so they don't migrate. But if the homing receptor is traffic through them, more than against the tissue. This is very reminiscent of the B cell as well. So activation T cell requires two signals. See, the first one is the C. Here's the T cell on top. Here's the T cell receptor. These are the CD3 chains that we defined. So these are the alpha beta chains of the T cell receptor. And then for the T cell receptor. And you'll see it's not just the antigen itself, but actually the MHC molecule as well. So what the T cell receptor sees is actually both of these together. It sees both the peptide to the MHC molecule around it. First signal is antigen. That sends a signal 1 through the T cell receptor to the T cell. Signal 2 is sort of analogous to the B cell. You have to have a second signal, and it's the second signal is received through this molecule. 28 comes up during T cell activation, and the ligand for CD28 is a bit confusing. Terminology. They used to call it 7, 7-1, and 7-2. Now they have a CD number, so CD80, CD86. Sorry about it. It's the co-stimulatory molecule that's found on the antigen receptor cell. And it's CD28 produces signal 2. So a combination of antigen signal 1 and co-stimulation signal 2 allows that T cell to become activated. And one of the consequences of that is that T cells starts to produce less than CD4 ligand. It's a very important molecule for having. Signal 1, signal 2, both can get T cell activation. So each of these are associated with signaling cascades. And the two of those cascades together is the required. It won't activate itself properly. I showed you the signaling cascade for both of them. If you have signal 1 without signal 2, you practically say that. Sequential. CD28 comes up on this one. And then that then receives co-stimulation through. So as I mentioned, signal 1 without signal 2 doesn't work. You have to have both signals. The activation of the main receptor. So this is the first time. Chemical cells between the innate system and the adaptive system. Remember that every cell it's able to respond to pathogen. So the responsibility of the whole immune response is controlled because it can cause damage to this. So the responsibility of that is on the shoulders of the body. So that cell is very important. We've encountered these different T cells already. These are the different CD4 subsets. So we actually start out with an activated T cell. Determining which way that T cell becomes is a little bit tricky. Largely depending on that is dependent on things like the T cell. It's a very tightly orchestrated process. It's dependent on what we call fate specified something. So gamma interferon producing Th1 cell requires gamma interferon IL-12, Th2 requires IL-4 and so on. T cells must be turned off again. Well, the CD28 stimulatory molecule that's fixed. This co-stimulatory molecule on the T cell. So this is the receptor for the co-stimulatory molecule CD28 that we're looking at. Quite a positive signal that allows that T cell to develop. But after a few days, we start to see another receptor which is called CTLA4. So binds to CD8 and CD86. Our affinity for CD8 and CD86. So it tends to outcompete CD28. CTLA4 is an inhibitor. It does it, so it does the opposite. CD28. It actually turns. Remains. This is an inhibitory molecule. Some tumors that express but kill tumor cells, but they're a blocking antibody. Those T cells. So the antibodies actually block CTLA4. Signals with tumor cells. So there are studies now that use antibodies against C. And immunotherapy. Okay, so we now have to switch gears a bit. We have to look at the other side of the equation. We'll look at the T cell receptor. We're going to spend the last few minutes just looking at it. This is, as the name suggests, was actually discovered through tissue grafts. Histone is tissue compatibility means tissue grafting initially of mice. But every vertebrate has an MHC. And the human one is called a large stretch of DNA with 3.6 megabases of DNA. Not only does it encode the MHC molecules, it also encodes other genes that we're not processing presentation. So anyway, the class 1 MHC molecules in humans are called HLA, A, B, and C. So those are the class 2 molecules are called HLA, D. DR, DP, DQ, HLA, A, B, and C, class 1, DP, DQ, DR, class 2. We've already heard now that these MHC molecules, they present antigen to the T cell receptor. With some diagrams, both of them. C1 has what's called an alpha chain that has 3 domains, and that's encoded in MHC. Some of chains for P2M or P2 microglobulin. Class 2, superficially looks very similar, although the chains are different. Actual diamond fills it up, and both of those chains. HC1 presents peptides T8. Awesome. And if you look at histone structure, similar superficially, you can see this is kind of T cell receptor IU looking down on the MHC molecule, and you can see the peptide is sitting in this cleft from where the really the only difference is the peptide that's presented by MHC molecule is a little bit shorter than the peptide presented by MHC2. That's really the only. Let's talk a bit about how the antigen gets there. Well, so MHC class 2 molecules, those present peptides derived from extracellular. So here's a cell that expresses class 2 MHC molecules. Cell macrophages in B cells, only cells that express MHC2. What they do is they take up extracellular antigen, fertilized into the cell, and it's broken down in this endosomal enzyme, breaking down peptides. At the same time, these MHC class 2 molecules are being produced inside the cell. They make their way up through the Golgi, break loose these transport vesicles, and then they fuse with the same compartment containing the peptides. And then the peptide will bind to that peptide binding molecule. And this is displayed. One is slightly different. So class 1 molecules. Class 1 molecules are found on all nucleated cells. Remember class 1 is the family of CD8 cells. All nucleated cells have the capacity to kill if they become infected or every nucleated cell in the body has class 1 on the surface. So tumor cell or virus infecting. So those antigens actually start out like cellular antigens, the tumor antigens, the viral antigens, the cell that's infected. Those antigens start out like within the cell. Those are then broken up into peptides by this big multi-catalytic complex called the proteasome. A big collection of proteolytic enzymes. Those peptides come out the other end, transported into the picked up by MHC1 now. So a bit like the MHC class 2 that expresses in the Golgi, where they encounter the peptide. They pick up the peptide and transport it to the surface. Antigen processing pathways, extracellular and intracellular. Extracellular antigens are processed to present two cellular antigens. We've already seen this. This is MC2 on the surface of macrophages. That's one of the 3 antigen-presenting cells. Remember, these cells take up bacteria, they break it down, they do a fairly okay job, they present peptides and can't quite eliminate all of the intracellular bacteria, so along comes a Th1 in the cell, has the appropriate T cell receptor, recognizes that peptide, and acts. There's a respiratory burst inside the macrophage, antibacterial. Can't really do that very well without emotions. Another one, the B cell. We've seen every cell, we've seen macrophages now. Finally, B cells. So two things happen. One is that the T cell first gets activated by this the living cell, T helper cell, TFH cell. That you take, in this case, we're looking at a virus. So the virus is taken out, it's broken down, at 5%. Meanwhile, on the other side, you've got a B cell, which has a B cell receptor that recognizes the same virus. Two internalizes the antigen, breaks it down, and stem cell compartment. Virus derived from cells to class 2, and then present the surface. Now we have B cell and a T cell that recognize the same virus. They recognize the negative. They'll get together because this class 2 molecule on the surface of the B cell is presenting this exact same peptide that this T cell saw when it was primed initially by Davies. So this, now we have this interaction between the B cell and that primed cell. Cell recognizes the same peptide that it was primed against. But this time it's the cell, and now the B cell gets activated through cytokines and base stimulation. Ensures, because the B cell is an antigen presenting cell, it ensures that the T cell delivers help to the correct B cell. Because those have any B cells, they only help with the B cells that display the peptide. These MHC molecules, they cope with C molecules use a slightly different method, and they resorted to using polymorphism. Variety of different alleles and their integration. So if you look at the class 2 molecules, there are 1,200 different DR chain, over 1,200 alleles in human population. Class 1 MHC molecules, known as A, B, and C. Even more polymer, there's thousands of them out there. What you do is you inherit one of each, one from each parent. Typical occasion. So HLA 1, 18.4, beta chains 3 and 7. So everybody has their own very confident alleles in the population. Those alleles you inherit. If you're going to have a tissue transplant, they have to be matched. But the kind of MHC haplotype that you inherit can determine how responsive you are to this people are susceptible to this. Might not have the right MHC molecules presented. So it's long been recognized that the immune response two human alleles, because it's genuine textbook. We take 2 class 1 MHC alleles, A2 and A68, and we line the sequences up. Differences on the two-dimensional structure. Those differences are those polymorph in and around the peptide. The rest of the molecule is very concerned because it has to interact with those. Same thing with class 2 molecules. So those polymorphisms, those slides reflect. I don't have a slide to show you this, but those determine what peptides will be presented by your MHC. So each allele can present thousands of different peptides. They only have to have like one or two then, so the rest of the so, those MHC molecules are very promiscuous. They can present thousands of MHCs. At some point in human evolution had provided some positive benefits, some fitness against a particular factor. For example, HLA-B53 is thought to have played a major role in checking this. And we still have a lot of people. If it wasn't useful, a lot of these are very different from the way antigen checkers do it. Finish up with a bit of timing with a bit of clinical stuff. So the MHC is what its function is to present foreign peptides to T cells. Doing tissue transplantation. Now, tissue transplantation is a different matter. Tissue graft, but that was how it was discovered. So if you take these are inbred strains of mice now, which means that they're all genetically identical, separate. For the most part, those mice are genetically identical. You can take a tissue graft from one strain of mouse, put it in the same strain. As long as it has the same MHC, so it's shown as MHCA, yellow, that graft is tolerable. However, if you take a tissue graft from that same strain and put it into an unrelated strain that has a different MHC, that graft is rejected very rapidly. Now, conceptually, it's quite difficult to understand why it happens, because it's got nothing to do with peptide building. I don't think I even understand that. MHC molecules which are not what your T cells have been educated, what are called allogeneic MHC molecules, then those T cells go crazy. It's got a very different mechanism to the normal mechanism of MHC molecules. Nevertheless, this is what happens. And you can actually take mice here that have the same MHC but a different background. So, for example, it might be and you can take that tissue transplant, put it male transplanted with attached to the MHC, but still slowly rejected. That actually is more like a conventional mode. What's happening is that there are antigens in males that are not found in females, in peptides. Like in those male antigens, they're actually presented by the female MHC. I am just so even though you get a perfect match at the MHC, you can still get slow rejection. Take a look at it. So in humans, the same thing happens. You've got a kidney graft. And those dendritic cells, once they're transplanted into the host, can find their way into lymph nodes. And then those dendritic cells will activate the T cells in the patient. And this is a very vigorous allogeneic T cell response. Okay, these are not leave the lymph node and they'll go destroyed. So if the tissues are not matched with the MHC, then so what we try to do is match as many of the allele MHC pairs as possible. But even low rejection for the ion. These drugs, these immunosuppressive drugs, will still require access to the I just look at graft versus host disease, which is kind of the other way around. Instead of the transplant, here the transplant tries to reject the host, and it's called graft versus host disease. And this often happens with bone marrow. And these are widely used to treat lymphoma. The host will first have some kind of treatment to remove his or her own hematopoietic stem cells. The idea is we want to replace the recipient's bone marrow. The recipient's bone marrow is killed off using radiation chemo. Donor T cells, donor bone marrow is then rejected. There are T cells in that bone marrow graft that the recipient receives. Those T cells will then get activated and then those T cells in the already damaged a little bit and inflamed by radiation treatment. So they're attracted to these inflamed areas, and then those effector cells that came in with the bone marrow will actually try to kill the cells in the skin and get activated to the rash. And of course, we try to achieve as well as we possibly can. But again, or even if you do get good matching, these are survival plots. But in red, survival is never 100%, even if you have a perfect match. It's the same with graft versus host. You still get some appearance of GBH in graft versus host, even if you've got a good match. These foreign peptides that are presented by the host male cells being introduced into make these anti-tumor T cells, trying to get T cells to kill tumors with a perennial problem. You never really know what the tumor antigen is. But there are lots of this marker. This is a cell marker, so lots of tumors like ALL, for example, express CD19. Should be used therapeutically using what are called CAR T cells. So CAR stands for chimeric antigen receptor. So you can take the variable domain and antibody. And you can create molecules of those antigen binding domains with the intracellular signaling domains of the different chimeric antigen receptors into T cells, mainly CD4 T cells. These CAR T cells, the T cells will turn to they'll recognize the actually through FDA approved to customize and actually provide your but sample and intermediate lab material. Construct. Those T cells go in the lab and feed back in again. With only one should go tumors. Finish then, just a little summary. So T cells develop in the thymus. They generate this repertoire of T cell receptors using rearrangements. On the binding with high affinity to the thymus killed off, it's negative selection. We look processing pathways, MHC1 and MHC2, present